Welcome to Everything Matters, Tales from the Periodic Table. I'm your host, Ron Hipschman, and today we're going to talk about the element tin. Tin is a very interesting element. Here I have a beautiful shiny sample of tin. You could see that this is actually a pretty large sample. Let's get back to our presentation though. Here we see the beautiful periodic table produced by Theodore Gray. Incidentally, Theo has written one of my favorite books called The Elements, which you can pick up from the online Exploratorium store if you want your own copy. Check out his fantastic website, periodictable.com. Tin is the 50th element in the periodic table. Its atomic number is 50 because that's how many protons are in its nucleus, and that's what distinguishes it as a unique element. We have no idea who discovered tin, but it may have been found as early as 3000 or 3500 BCE. It was probably not known as an independent element that early, but rather in combination with copper. More on this combination, called bronze, later. There are about 9 elements discovered before written records. Here you see which ones: sulfur, iron, copper, silver, tin, antimony, gold, mercury, and lead. These elements were discovered so early because many of them occur in nature in their native state. Tin derives its name from the Latin name stannum, which originally meant an alloy of silver and lead. Of course, we know that tin is neither silver or lead, but rather a unique element on its own. Stannum gives us the chemical symbol, Sn, for tin, and we still use names like stannous chloride for chemical compounds that contain tin. Through unknown translations, stannum became Zinn in German, or ten in Swedish, and finally by the 4th century, tin from the Dutch. Tin has 2 main allotropes. Allotropes are 2 or more different physical forms in which an element can exist at room temperature, like graphite and diamond for the element carbon. Tin has 2 allotropes. The first stable allotrope is beta tin on the right, a silvery white malleable metal which has a body-centered tetragonal crystal structure. At lower temperatures, beta tin transforms into the less dense gray alpha tin on the left. This has a diamond cubic crystal structure. Both are still pure tin, but the atoms have a different arrangement. Here's a sample that has both allotropes. You can see both the brighter beta tin and the grayer alpha tin. You can turn silvery beta tin into darker, more brittle alpha tin simply by lowering its temperature to less than 13.2 degrees Celsius, or about 56 degrees Fahrenheit. You'll notice that the volume of alpha tin is larger, 27% larger to be precise. This movie is sped up by a factor of 28. This process is called tin pest. It's also been known as tin disease, tin blight, or even tin leprosy. In 1912, Robert Scott trudged toward the South Pole to find out that previously stashed cans of kerosene fuel were empty. The cans had been soldered with tin. In the low Antarctic temperatures, it's hypothesized that the soft and ductile tin solder holding the cans together had turned into brittle alpha tin, allowing the contents to leak out. Another interesting effect can be heard when a bar of tin is bent. The crystal structure of tin is distorted, and the dislocation of the crystals can be heard as a crackling sound, also called a tin cry. The universe produces most of the tin, 69% of it, in dying low-mass stars, with smaller amounts, about 31%, produced in merging neutron stars. Pretty exotic factory floor, I'd say. On Earth, tin is obtained chiefly from the mineral cassiterite, which contains stannic oxide, SnO2. Cassiterite is the only commercially important source of tin. The main suppliers of tin are China, producing 42% of the tin in the world, followed by Indonesia with 28%, then Peru, Bolivia, and others. In the U.S., we import 77% of the tin we use. The American Chemical Society's endangered element list places tin as, quote, limited availability, future risk to supply, unquote. So we need to keep our eye on this and be sure to recycle our tin. This rating indicates the relative risk to the supply of tin required to maintain our current economy and lifestyle. How common is tin? Not super common, but not super rare either. It's the 48th most common element in the universe, the 39th most common element in the sun, the 38th most common element in meteorites. In the Earth's crust, it holds 47th place, about 2 parts per million, compared with 75 parts per million for zinc and 50 parts per million for copper. In the oceans, it's 51st, the 51st most common element. And in humans, surprisingly, it's the 26th most common element. The current cost of tin is about $18 per kilogram. Over the past couple years, that price has gone up and down, but not wildly, from a high of about $22 per kilogram to a COVID-19 low of about $13 per kilogram. If we compare the size of the tin atom to that of hydrogen, we'd see something like this. The tin atom is a little less than 3 times the size of hydrogen. By the way, a picometer is a trillionth of a meter. Atoms are very small. Here are the atom sizes sorted from largest, cesium on the left, to smallest, helium on the right. Tin is a mid-sized atom. Each element has many different forms. For each specific element, the number of protons in the nucleus is the same, 50 protons for tin, but there can be different numbers of neutrons in the nucleus. All these different forms are called isotopes, and they're chemically identical to each other, but with slightly different weights. The number you see next to the chemical symbol is the total number of protons and neutrons in the nucleus. There are 39 isotopes of tin, and of these there are 10 stable, non-radioactive isotopes. More stable isotopes than any other element. These 10 stable isotopes are found in different proportions in nature, from 0.1% to almost 33%. By the way, the word isotope comes from the Greek isos, meaning same or equal, and topos, meaning place, since all of these various forms of tin occupy the same place in the periodic table. Of the radioactive isotopes of tin, these are the longest lived, the ones with half-lives over 1 hour. More about half-lives in the next slide. As you can see, the longest half-life here is 230,000 years for tin-126. Even 230,000 years is but a blink compared to the age of the universe, so any tin-126 or other tin isotopes cannot be left over from the Big Bang 13.7 billion years ago. These isotopes must be manufactured in stars or reactors. What's a half-life? This graph shows an exponential decreasing curve. As an example, say we start with 1,024 atoms of the isotope from the previous slide. You'll see why I chose 1024. Hint, it's a power of 2, and we'll be doing a lot of divisions by 2. If you wait one half-life, half of your isotope will decay, and you'll have 512 atoms left. If you wait one more half-life, half of that half decays, leaving you with 1/4 of the original 1024, or 256 atoms. Another half-life, half as many again, or 128 atoms, and so on. After 10 half-lives, you'll have about 1/1000th of your original amount. By the way, notice there's one remaining atom after 10 half-lives. If you waited one more half-life, your remaining atom would have a 50-50 chance of decaying in that time. Tin is a moderately dense element at 7.31 grams per cubic centimeter, the exact same density as our previous element, indium. As a reminder, water has a density of 1 gram per cubic centimeter, and I've put up a couple more densities for comparison. Iron is slightly denser than tin at about 7.89 grams per cubic centimeter. Here's a graph of the elements from highest density to lowest density. When we do this talk at the Exploratorium, we have a set of blocks so you can feel density for yourself, but we'll have to wait to do this until we're back in the museum. Our set of blocks have a wide range of densities, with the densest at tungsten, to lead, to copper, to iron, to titanium, to aluminum, to magnesium, and we also have plastic and wood blocks, but those are not technically elements. Again, tin's density, the magenta circle, is 7.31 grams per cubic centimeter and is the 44th densest element. Tin has the 78th highest melting point, a fairly low 232 degrees Celsius, or 450 degrees Fahrenheit. There are only 11 other solid elements with lower melting points. As you'll see in a bit, because of this low melting point, tin is used in some important applications like soldering. Tin has the 46th highest boiling point at 2602 degrees Celsius. That's 2373 degrees C above its melting point of 232. A pretty big difference between melting and boiling. Tin has the 16th highest thermal expansion rate. It expands 1 part in 45,454 for every degree Celsius in temperature rise. That means if you had, say, a 1 meter bar of tin, it would get longer by about 22 10,000ths of a meter, or 2/10ths of a millimeter, when you raised its temperature by only 1 degree Celsius. That doesn't seem like much, but it would add up if you change the temperature significantly, or you have a long bar of tin to start with. Iron expands about half as much for the same temperature change. Tin is very soft, with a hardness of only 1.5 on Mohs scale of hardness. Even though it's on the same line as our previous element, indium, tin is a bit harder. Mohs scale is a bit rough. In this chart of hardness, sorted from hardest, boron on the left, to the softest, cesium on the right, tin is the 52nd hardest, or rather the 15th softest element. You could, with some difficulty, cut it with a knife. Tin is the 26th best conductor of electricity. Not bad, but not good enough to use it for this quality, although tin does become a superconductor at 3.72 degrees above absolute zero, a better conductor than any element at room temperature. It's the 28th best conductor of heat. Again, not bad, but not excellent either. From our periodic table of the spectra, we see that tin displays a variety of emission lines, but lacks much on the blue and violet end of the spectrum. Putting a solution containing tin into a flame displays a beautiful blue color, which actually kind of surprised me given the lack of blue emission lines in its spectrum. I guess that it's easier to excite this line in the spectrum of tin from unexcited room temperature atoms. Let's take a look at some of the major uses for tin. There are many of them. These are the primary uses for tin. The largest by far is in soldering, followed by plating, chemical uses, alloying, glass production, and other uses. Let's take a look at these. Because of tin's low melting point, it's used extensively in the electronics industry to solder metal parts together. Here, you see electronic parts being soldered to the copper pads on a prototyping circuit board. Plumbers use solder for the same purpose, to solder together copper pipes. Up until 1986, most solder contained 60% tin and 40% lead. Many people thought that soldering together drinking water pipes with lead-containing solder may not be a very good idea, so that was outlawed, and in 2006, many countries, and California, banned lead in electronic solder too because it was beginning to appear in landfills. We now use lead-free solder that is a combination of 99% tin, 0.3% silver, and 0.7% copper. Speaking of low melting points, let's look at a couple more interesting examples. Fields metal, named after its inventor Simon Quellen Field, is a eutectic alloy. The word eutectic comes from Greek eu, meaning well, and Texas, not the state, meaning melting. Well, maybe that's not a bad description of the state after all, but I digress. A eutectic alloy melts at a temperature lower than the melting point of any of its ingredients. Note that all the ingredients of Fields metal melt above 156 degrees Celsius. Fields metal is a solid at room temperature, but becomes liquid at the low temperature of approximately 62 degrees Celsius, or only 144 degrees Fahrenheit, less than half the lowest melting temperature of any of its ingredients. It's an alloy of indium, bismuth, and tin in the percentages you see here. An even more impressive example of a low-melting eutectic alloy is Galinstan, which gets its name from its ingredients: gallium, indium, and tin. Remember, the old name for tin was from the Latin stannum, which is the stan in Galinstan. Galinstan is an alloy of 68.5% gallium, 21.5% indium, and 10% tin. It remains a liquid below the freezing point of water. Its melting point is minus 19 degrees Celsius, or minus 2 degrees Fahrenheit. Galinstan can be substituted for mercury in thermometers, since it's now illegal to use toxic mercury in medical thermometers. Tin plating, the second largest use of tin, is perhaps most familiar in the canning of food. The cans themselves are made of steel, and we all know that steel has a rusting problem. By plating the steel with tin, which is non-toxic in its metallic state, the cans can no longer rust. So calling these tin cans is a bit of a misnomer, but there is tin there. Tin cans aren't the only food-related item. Here is a beautiful tin cup from Theodore Gray's amazing Element collection. One of the chemical uses of tin is in toothpaste and mouth rinse in the form of stannous fluoride. Stannous fluoride is added to these products as an antibacterial agent that's clinically proven to protect against gingivitis, plaque, tooth sensitivity, in addition to preventing cavities, and is no doubt approved by 4 out of 5 dentists. Some products substitute sodium fluoride, which only protects against cavities. With its low melting point and low toxicity, tin is a good candidate to use in casting. Here we see classic tin soldiers and a tin caterpillar for good measure. Tin coins have even been known, though with the easy melting and casting properties of tin, they were probably simple to counterfeit. I have no idea of the monetary value of these coins, but I'm assuming they are worth less than the total cost of the tin they're made from, making counterfeiting uneconomical. The other problem with tin coins is tin pests. If you keep your money at a low temperature, you won't have any after a while. Just alpha tin crumbles. Aside from the eutectic alloys we've previously seen, tin has been an important ingredient in many metals since ancient time. Here you see two bronze examples, the Huumu Ding, or sacrificial vessel on the left, the largest surviving piece of bronzeware from around 1100 BCE, and on the right we have a bronze statuette of Jupiter from the second half of the 2nd century CE. In the middle, a different alloy, a pewter mug. The first tin alloy used on a large scale was bronze, as early as 3000 BC. The giant bronze dirk from 1500 to 1300 BCE on the left is a very early example. Bronze is still used in contemporary statuary, such as Rodin's The Thinker, which you can visit in the Legion of Honor here in San Francisco's Lincoln Park. Bronze is an alloy of about 87.5% copper and 12.5% tin, though the percentages can vary depending on intended use. The addition of tin, and sometimes other elements to copper, create a metal that was harder, easier to cast, and more durable than any of its constituent ingredients, and harder than any other metal up to that point. This invention led to the Bronze Age. Pewter is a malleable alloy composed of 85 to 99% tin, mixed with approximately 5 to 10% antimony, 2% copper, bismuth, and sometimes silver. An extremely important use of tin is in the manufacture of plate glass. Until 1959, it was fairly difficult to manufacture very flat glass with parallel sides. In that year, the float glass process was invented, and it uses tin, lots of tin, as part of the glass forming process. Raw ingredients are combined and added to massive furnaces at the start of the process to blend and melt what becomes glass. A ribbon of glass exits the furnace to the tin float bath. Glass is less dense than tin, so like oil and water, the glass ribbon floats on top of the perfectly flat molten tin surface. It's drawn through the bath by a set of rollers on each side of the ribbon. Pulling the glass faster thins the ribbon. Slowing the rollers makes a thicker sheet. It exits the tin bath into what's called the layer, which, in the next 800 feet, gradually cools the glass, reducing stresses within the sheet, creating a strong piece of glass. The ribbon is then inspected, cut to size, packaged, and shipped to the end user. Here's a photo of the glass ribbon passing through the tin float bath. You can't really see the tin since it's glowing the same red color as everything else in the chamber, but you can see the toothed wheels that draw the glass along. Given the linear nature of the float glass process, these plants tend to be very long, usually extending a quarter mile or more. There are about 450 of these float glass lines in the world, producing over 1 million tons of glass every year. None of that would be possible without tin. This glass finds its way into architectural uses, the automotive industry, the solar panel manufacturing industry, and the making of glass for display panels, like the one you're looking at right now on your phone, tablet, computer, or television. Speaking of display panels, tin plays another important role in those. Indium tin oxide, or ITO as it's referred to in the industry, is a clear conductor of electricity. Let me say that again. It's a conductor that you can see through. It's used in applications such as liquid crystal panels. You see an extreme close-up of an LCD panel on the bottom right, with live video from my television on the top. Let's look at a cross-section. Electrical current must flow between the light blue electrodes in front and behind the liquid crystals. The liquid crystals can switch between transparent and opaque when placed between the transparent ITO electrodes. Light from the light source on the back side of the panel must pass through the ITO electrodes and the liquid crystals. Normal conductors, like copper and aluminum, are opaque and would block the light. Indium tin oxide is both conductive and transparent, so it's a natural for this application, allowing the light to pass the liquid crystals and then through the red, green, or in this case, blue colored filter in front to get to us. Another application of liquid crystal displays is privacy glass that can be almost magically switched from opaque to transparent. This example in the bathroom is from intelligent glass. You can't do this without the transparent electrodes made from indium tin oxide within those panels. By the way, this isn't cheap, around $50 per square foot, so this example would cost you about $8,000. Before the laser printer or the inkjet printer, letters were placed on the page by pressing inked pieces of metal with letters molded into them to the paper page. Each letter was laboriously placed, one at a time, into a frame called a chase. These letters, or type as they were called, were made from a low-melting but strong alloy consisting of 50% to 86% lead, 11 to 30% antimony, and 3 to 20% tin. The formula changed depending on the usage. If you ever went into a printer's shop, my dad was in printing, you'd see type cabinets like these, with drawers, each containing a specific font at a certain size. The drawers were organized in some way that made sense to printers, but I could never really figure out. Slightly less laborious were linotype machines. Here, the operator sat in front of a keyboard and typed the text. Liquid type metal was instantly cast into lines of type that were then mounted in the printing frames. Far less work than dealing with each letter individually. Tin plays no natural biological role, but is found in the human body in small quantities, usually from the environment and probably from some of those tin cans. Metallic tin is relatively non-toxic and passes through the digestive system with extremely little absorption. However, indium tin oxide, used in those LCD panels, can cause harm in your pulmonary and immune systems, so exposure in LCD manufacturing must be monitored. We'll end today's talk with Mary Soon Lee's elemental haiku about tin. Your magic number, a secret no one could guess back in the Bronze Age. Thank you for watching Everything Matters, Tales from the Periodic Table. The next program in this series will examine another interesting element, antimony. We hope you'll join us. This program, like all Exploratorium programs, is only possible because of donors like you. We know that this time is challenging, but if you can, help us keep educational content like this free and accessible to all by donating today at www.exploratorium.edu/connect. Thank you.